Hi, good afternoon, everyone. We're excited to share how we use Ray to train 3D foundation models at Roblox. So I'm Steve from the ML platform team, and joining me on stage are my teammates Liangjun and Yiqing. So I want to start by asking a question. What would you like to create today? And it's not a rhetorical question because I thought it would be fun to start this talk with a demo, even though it's a bit unnerving as a presenter. So we're in Roblox right now, and I'm just going to get this ball rolling by creating a battle mech with 4 wheels for now, and maybe also an alien monster gun. Does anyone have any other ideas on objects you can generate? And this is our 3D foundation model. It can just pretty much generate anything you want. You can just shout it out. There you go. Okay. All right. Well, let's start with this one. So a cute alien car with 4 wheels. All right. Anyone else?
Try an air fryer.
An air fryer. Okay. Want to make it more creative, or just a normal air fryer? Okay, just a normal air fryer. Okay. Anything else? Get creative. Okay, well, let's see what it's doing. So we have this mech already generated, and you can see it's not only just a 3D mesh, it also has textures, and you can also drive it, you can interact with it. So our model is called the Cube 3D model, and it's open source, it's on Hugging Face, you can play with it, and we just open sourced it recently, so it does all of these things and also make it interactive. And our gun should be coming in as well. And there's the air fryer, which is very standard, nothing crazy. Okay, any crazier ideas? Like an NPC? Okay, what do you want it to be like? A ghost? Oh. Okay, K-pop. We've seen that example before, right? In a different talk. Demon Hunter. Okay. And we have this alien car right here, which is very cute, as you asked for. We can drive it as well. Yeah, so let's see if the NPC will spawn in pretty soon. Okay, actually, I'll probably just skip this for now for time while it's being generated. So yeah, so we just saw was our first step towards a vision, towards a world where you can just kind of ask whatever you want, and then co-create it with AI. And in the future, you should be able to just change the scenery with just a simple prompt. But delivering this vision at Roblox scale presents an enormous engineering challenge. So for those of you who don't know Roblox, we are an online platform that everyone comes to play and create and connect with each other every day in all kinds of virtual experiences made by our global community of builders. We recently surpassed 150 million daily active users, 45 million peak concurrency, and our ML platform serves over 1 million QPS across 400 models running in production. So you may be asking, why does Roblox need ML? And we get this question a lot, but there's actually a lot of interesting use cases. First and foremost, safety is core to everything we do. So we have a model that moderates billions of pieces of content per day across 25 languages, all in real time. We also embed AI as a partner for our creators, so we have code assistants and also AI texture generation. And finally, I'm sure you saw this coming, we use AI for search and recommendations for our players. So this is an ML platform conference. Let's talk about the infra behind all of this. It's pretty complex, but we're just going to focus on this tiny little rectangle right here, which is distributed training and also batch inference with Ray. We'll start by talking about our Ray development infrastructure, how we train the foundation model, and then we'll talk about the compute infrastructure that powers all of this. So how do we iterate on Ray jobs quickly? We'll talk about our evolution of Ray iteration speed at Roblox from slow to quick. So initially, we created the Ray infra for production jobs. This means that we are building on top of the KubeRay and KubeRay API server. We have our own front end, which integrates with Kubeflow, and we have a back end, which provides auth, and also an abstraction layer over our SDK, REST API, and UI. But whenever you want to change your code, you have to rebuild the Docker image and relaunch the job. And I'm not sure how it is at your companies, but our researchers hate this so much. And by the way, we also, as our commitment to open source, we've contributed our UI to the KubeRay project as the KubeRay dashboard. It's built with Next.js, React, and TypeScript, and thanks to the community's contributions, it's now compatible with KubeRay API Server v2. So if you want to have a quick way to visualize your Ray jobs, this is a great thing to try. So yeah, next step. We added the ability to snapshot your code using an SDK to an S3 bucket, and that will be pulled on the runtime of the Ray job, so you don't have to build Docker images as much as before. But you still have to wait for the job to spin up, which takes some time. So that leads us to a persistent cluster. So here we have a code server UI running on the Ray server's head node, and you can directly iterate on code in this VS Code experience in the browser. We also have an auto-scaling group of GPU workers that can scale to 0 if you're not using the GPUs. To expose this UI security and also like the Ray head node dashboard, which is great for debugging, we use an Istio configured Envoy sidecar to enforce the auth policies, which is created by the Kubeflow profile controller. So initially, we actually used Istio MTLS on all the communications between the Ray head and the Ray workers. And it was causing some problems because it was slowing down the jobs. We have some jobs that slow down by 10x. And it also means that we have to expose so many ports that Istio has some OOM issues in the sidecars, which took down our prod cluster a couple times. So that was unfortunate. And there was actually a talk I went to yesterday by Workday that also mentioned the same issue. So I regret not seeing that before. Right, so like our solution was to essentially disable the IP tables on the Envoy sidecar and only proxy the ports that we care to expose, and we can make them secure. So our engineers want to use their own local IDE tools, and that's where Coder comes in. So Coder is this cloud development environment project, which usually provisions a pod on Kubernetes, and then runs the Coder agent on it to create an SSH tunnel to your laptop for local IDE development. We can easily adapt this to KubeRay by simply creating a Ray cluster instead of a pod, and then running the Coder agent on the head node of the cluster. We can map many Coder functionalities to KubeRay. For example, the auto stop feature can be mapped to the suspend field of the Ray cluster. So the cluster can be paused when it's not being used. And we can configure the Coder agent to scrape the Ray cluster status to display on the UI. And finally, we use Ray's excellent integration with UV to capture the packages and make sure they're present on the worker nodes when the jobs are launched. So here's what that looks like. You can create a new workspace. You can like choose H200 GPUs, and we'll have 4 or 5 of these workers. You can choose a Docker image. And as it's being launched, it will create a Ray cluster using KubeRay and then hook up all the Coder agents. You can see the status of the cluster being reflected on the UI, like the number of GPUs and so on. And I can open a cursor and just vibe code to my heart's content. And there's also the Ray dashboard as well. The adoption of Ray at Roblox has been tremendous. As everyone here knows, like foundation models have a huge, insatiable appetite for data, and we have fully migrated from Kubeflow pipelines to Ray for the Cube 3D data processing. For example, we have captioned over 100 million 3D assets using VLLM, which we contribute to, and I think our contributor is sitting right there, Roger. And then we also use the Ray Data LLM library. So we have, collectively as a company, we have launched hundreds of Ray jobs every day. And most of these Ray jobs are actually training jobs, which Liangjun will talk more about.
Hi, next I'm going to talk about how we leveraged Ray and the tooling Steve just presented to train Cube 3D, Roblox's own 3D foundation model. So first, I want to give a horizontal view of how we train model at Roblox. Since 2025, we have been using Ray Train as the distributed training framework to replace old MPI approach. To help machine learning engineers at Roblox to quickly onboard their use cases to the new platform, we built internal SDK on top of the Ray Train API to simplify the process of launching distributed training jobs to both AWS and on-prem clusters. First of all, we provide Docker images that take care of the container environments, including like network CUDA drivers based on the cluster hardware, and pre-installed essential packages like PyTorch and Ray. We use the idea of compute template a lot to allow users seamlessly choose from different combination of GPU type and amounts, which also helps the bin packing of smaller training jobs. In our SDK, we provide features like cluster sanity check, async checkpointing, and auto restart, which are beneficial for all distributed training jobs. After the job is launched, job owners can monitor the utilization and access logs easily on the UI as Steve demoed before. With the help of this internal SDK, we successfully onboarded all multi-node training job at Roblox to Ray Train. As you can see from this graph, Ray Train job, which is the purple bar, is now taking almost 2/3 of the GPU hours on our major development cluster. Next, I'm going to talk about the 3D foundation model and how we train this model with the help of Ray. When training this model, our biggest problem stems from the large size of our raw data sets. A typical 3D object raw file can be as large as 70 megabytes, and our data sets contains tens of millions of these files. Feeding the raw files to the model is unrealistic. We need to do heavy pre-processing of the raw files to get the usable data that the model can train on. This process can be both network and compute heavy. So to solve this challenge, we figure out two solutions. One is to use the Ray job to do the data pre-processing offline. So the other approach is more audacious, streaming and pre-processing the data on the fly as we train. We use Ray heterogeneous cluster to achieve this. In the offline pre-processing approach, we build a pipeline which basically downloads each raw file from S3, render the 3D object, and randomly sample points for several hundred times, then save the final results back to S3. Download and upload are network I/O bounded, while the rendering and sampling are compute bounded. Our V1 pipeline uses Ray data. Just like any normal pipeline, our pipeline runs very slowly in the beginning. To optimize this, we build V2 pipeline using the features from Ray code framework directly. We first separate the pipeline into components and try to overlap the network-heavy components with compute-heavy components so that we can achieve the max utilization on each node. For the downloading and uploading part, we use F5 CMD to maximize the network throughput. For the processing component, we use vanilla Python multi-threading to achieve the max CPU utilization. Most importantly, we use Ray's ad hoc resource feature to control and balance these workloads on each node to achieve the best overlap. As a result, we successfully reduced the data processing time by almost 75% and achieve a much better resource utilization. Although we optimized the offline pipeline, this approach is still a bit inconvenient. For example, if a researcher wants to try a new sampling algorithm, she needs to modify the pre-processing logic and run the whole pipeline from the scratch, which consumes both compute and storage. If we can do the pre-processing on the raw data set on the fly as GPU trains, this limitation can be addressed. However, to keep the GPU saturated, this approach requires a large network bandwidth and many CPU compute. And the resource on the GPU node simply alone is not enough. And the solution is quite intuitive. We just add more CPU nodes to the cluster and offload the major data loading to these CPU nodes. We build this solution, again, use Ray core framework directly. The first benefit is that Ray allows us to easily set up a heterogeneous cluster that consists of both GPU training nodes and CPU data loading nodes. Ray core API allows GPU nodes to launch async data streaming and pre-processing job on the remote CPU nodes very easily. Once the data is ready, it can be efficiently transferred back to the GPU node through Ray's object store. We rely on the placement group and ad hoc resource to achieve a better control of resource scheduling and workload placement. As you can see here, we utilize the CPU resource on GPU node to load data for 2 GPUs, while adding 6 extra CPU nodes to load data for the other 6 GPUs. This achieves one-on-one mapping between GPU and data loading workers and simplify the network topology. Finally, Ray allows us to horizontally scale the data loading by just adding more CPU nodes to the cluster, perfectly solving our network and CPU challenge to handle even larger raw data sets. Using this approach, we successfully achieved the same training MFU as our offline pre-processing approach. We keep GPU busy all the time while providing ML researchers a more flexible way to iterate algorithm and model. My colleague Yiqing is going to talk about how we manage our compute.
Now that we can develop Ray code and train our Cube 3D models, let's talk about the underlying compute infra. So as you can see on the left, we are dealing with 2 fundamental problems. First of all is the GPU availability. Getting access to the high-performance GPUs we need for AI and machine learning workload here at Roblox is a constant bottleneck. And secondly, relying on a single cloud is not always reliable. Whether it's cost, regional outages, or vendor locked-in, putting all eggs in one basket is a really risky strategy. So our approach is a 2-part strategy. First of all, we dynamically schedule workloads across both AWS and on-premises. This lets us burst to the cloud for machine capacity or use our own hardware for cost efficiency. We also abstract this complexity away. Researchers simply submit jobs without worrying about where the code is running. So this diagram is the overall architecture of our computing infra. I know it's pretty complicated, but don't worry. I will explain it in the next few slides. So first of all, users submit Ray jobs to a central control plane on our AWS EKS cluster. This manager cluster runs multi-queue, which is our federated job scheduler. And multi-queue intelligently routes jobs to 2 types of worker clusters. On the left is the elastic AWS EKS worker cluster. It provides cloud resources like the scalable node groups, and we also have H200 in our premium SageMaker HyperPod cluster. So on the right is an on-prem worker group holding our local powerful GPUs like the NVIDIA H200 and RTX Pro 6000. Each worker group uses cluster queues to manage team-specific quotas for CPUs and GPUs. And when a job arrives, multi-queue evaluates its requirements against the available capacity in these queues. And based on the configuration, it routes the job to the best available spot among the clusters, whether in the cloud or on premises, ensure the job lands on the correct hardware profile. And in summary, this architecture delivers a unified control plane for our decentralized hybrid cloud compute fleet. By pooling resources across clouds and on-premises, we increase both access to GPUs and system reliability, with no dependencies on a single cloud provider. So now let's discuss the GPU scheduling challenge. We were facing several critical problems. First of all, team needs quota for specific GPU types. For example, the model research team might need H200 for training, while an inference team wants L40S. And a generic NVIDIA.com GPU quota just doesn't work. Second, as you can see in the top chart, GPU usage was incredibly spiky. A team might demand a quota of 20 GPUs, insisting on immediate access, but in reality, they might just use it a couple hours a day or like few days a week. This combination leads to resource fragmentation. We had many nodes that were only partial used before, which means new pods couldn't be scheduled, even when we technically had some free GPUs. And from a user's perspective, this is very inefficient because they spend time just trying to figure out which GPUs were available and which ones they are allowed to ask for. And to fix this, we re-architecture our entire scheduling and queuing stack. Previously, team directly owned physical nodes in our cluster. We moved to quota as code. Resource quota are central managed in Git for queue cluster queues. Now, team owns a logical resource quota instead of the specific physical machines. And secondly, to resolve the fragmentation and usability problem, users no longer have to request a specific GPU model. Instead, they can put a range of the GPU types and tiers in their array job, such as tier 0 and tier 1. And tier 0 can preempt tier 1. And the system works through queue's native integration. Array job workloads specify the target local queue with labels. And queue uses resource flavor and workload priority class object to represent the GPU tiers that the user can use. And it will automatically inject node affinity rules and manage quota for the pods underlying the array job. And after resolving our large-scale GPU scheduling challenge, we quickly encounter a new bottleneck, that is the scaling speed. We discovered several root causes. First of all, array job pods were scaling slowly, and the underlying issue was the container image pooling. This created significant disk I/O bottleneck on our nodes and overloaded our central Docker registry. Each new pod attempted to pull the same large multi-gigabyte image, causing spikes in registry traffic and local disk I/O. And furthermore, getting reliable access to specific instance types, especially all those GPUs, was a major bottleneck that delayed our ability to scale, to place our pods. And the impact is visible in this pod start time chart. Before our optimization, average pod start time exceeded 8 minutes, with some even reach almost 17 minutes. This slow starts was unacceptable for users who expect their job to be launched rapidly. And to tackle these issues, we implement several optimizations. First of all, we optimize EBS volumes based on our benchmark for higher disk throughput and lower latency. Also, we implement a daemon set to pre-pull common container images, such as the NVIDIA device plugin, ensuring that the essential layers was available before the workload arrives. And for the array job image, we introduce peer-to-peer image distribution. Instead of every pod hitting the central registry, pods share common layers with each other, and greatly reducing pool times and registry load. We also leverage AWS SOC for our AWS cluster, allowing our container to start before the full image download finished, resulting in lazy loading and faster startups. The results are clear. As shown in this second chart, our pod time dropped dramatically from 17 minutes to a little bit over 2 minutes. So now we basically resolve all the three aspects for our platform. First of all is how to scale our GPU fleets. Second of all is how to schedule workload to the GPU fleets efficiently. And finally, how to scale our workload faster. Thank you, and we are hiring for our ML platform position. Yeah.
Thank you for all those insights and contributions. Okay, questions, raise your hand.
Hi, I saw a slide talking about the SageMaker Hyperpod. Can you share a little bit about the motivation behind you guys using that and what your experience has like?
Yes, so at that time, we are trying to get the H200, right, through the node group, AWS node group. But first of all, it's very hard to get, and the price was really high at that time. So we work with AWS team, like they give us access to the Hyperpod H200. We were among the very early group of user to HyperPod. And we also contribute some modification to, for example, cluster autoscaler, because at that time, cluster autoscaler doesn't support SageMaker really, really well. So we made few contributions on that area. But now, basically, SageMaker is similar to a node pool, but it's actually, they call it a cluster. We integrate that with our EKS cluster in order to use all those H200 machines. Yeah. So you don't use HyperPod anymore? We still use HyperPod, yeah. We have like HyperPod, regular node group, and also our on-prem data center nodes. Yeah.
Yes, thank you. Congratulations, very good presentation. If you could come back to the GPU scheduling slide, my question was like, since you changed your model to be quotas as a code, does that mean you have now like a pool of GPUs instances per week, per month? Do you ever run out of this pool? And will that also mean that every training job that becomes an on-demand pile in a queue for all to be executed in whatever instance is available? How do you manage the really high priority tasks that they need to run as priority as other on-demand jobs?
So let me try to answer this question. I'm not sure if I understand your question like clearly, but let me try to answer. So we have a Git repo. For each namespace, for each team, we have a profile, which in the YAML file, we specify, okay, how many H200, A100, for example, they can use as tier 0, and how many GPU hours they can use as tier 1, right? Then we have a controller, Kubernetes controller, to sync that to our Kubernetes, right? So it will build all those like cluster queues and all those like local queues. So using queue, we can basically schedule the workload based on with the priority workload class to schedule the workload to our cluster. Yeah.
So these tiers are like the levels of priorities that how the job should be attended to.
Yeah, exactly.
Okay.
And all those, so basically we use this management system for the H200 and A100. All those nodes we already reserved. So all those are not like on-demand nodes. Yeah.
Cool, thank you. And do you ever run out of this pool? And do you need to require more instances? I'm just curious.
Sorry, could you please repeat?
Yeah, if you ever run out of instances, GPUs, and you need to require more from the business.
Yes. So basically, we just purchase more, like, for example, HyperPod node group and onboard more machine to our on-prem fleet. Yeah. And we have a dashboard to show all the utilization.
Yeah, hi. Thank you for the really great presentation. I had a question regarding the online processing. Is there a particular reason you went with Ray Core versus Ray Data map batches? It seems like map batches can solve a lot of those needs.
Do you mean this slide? Yeah, so I think with Ray, we first tried Ray Data, then we use Ray Core directly. With Ray Data, I think we run into several issues. Like, for example, we don't have a very granular control of which workload ends up on which machines. And we do want to have this kind of granularity of control. So as I just showed, we want to achieve a one-on-one mapping between the CPU node and each individual GPU. We want a CPU node to work entirely for one GPU. So these kind of features we can only implement using Ray Core. And we also know better of how everything works under the hood. So that's the main reason why we use Ray Core directly.
Hi. So I was wondering if you also tried the same approach with any other 3D generation models instead of Cube 3D with, like, say, Trellis or similar models, which also generate a lot more realistic assets, but they have, I'm guessing, a latency factor. So did you try the same technique with any other 3D models?
Yeah, I think our researcher teams has already published a tech report about the model, the architecture, and how it is different from the other, like Trellis you mentioned, like all other 3D generative models. I would encourage you guys to take a look. But I think a big difference is that our model right now is autoregressive, while most of the other models are diffusion-based.
I think that's all we have time for. You can come up and speak to the speakers afterwards if you'd like. Thank you, everybody. Thank you for the presentation.